So, example number 3, we're going to calculate the total distance traveled. So, example number 3 is just an extension, really, of our original problem. So, just to kind of remind you guys, we didn't know what S of t was, but we were given that the velocity as a function of time was this. All right. And for example 1, we did some math. For example 2, we did some more math. And so now we want to figure out the total distance. All right. So example number 3 wants us to figure out the total distance that was traveled. And we kind of did that in example number 2 because, well, I kind of went beyond. So we're going to start from scratch on example number 3. Well, to be honest, because the video for 1 and 2 didn't work out so good. So, yeah. So to find the total distance from this thing, essentially what we have to do is we have to evaluate it from 0 to 5. So remember in example number 1, they said that, well, let me just restate it. Example number 1 said, there's a particle in motion. It moves in a linear path. Okay? The model or function of the velocity is going to be v of t as a function of time, t squared minus 8 all over the quantity t plus 1 raised to the second power. Okay? And then they asked us a bunch of questions like what position will it be in at 1 second? What position will it be in at 5 seconds? What position will it be in at 0 seconds? And we determined that in order to find the position, you kind of had to do the antiderivative of the function v of t. And we looked at it graphically, and then we did it analytically, and we evaluated it at the different points that they asked us to. And so now they want to know the total distance that was traveled. Now, here is a, the way that they word this when they say total distance is interesting because we could do this rather quickly on our calculator. So, if you remember on example 1 and 2, we basically did the antiderivative of this. So if I go from 0 to 5 of t squared minus 8, and I'm going to rewrite this as t plus 1 raised to the negative 2. On the next line, what I end up with is the antiderivative, which is going to be t to the third power divided by 3 minus 8. This quantity here, t plus 1 to the negative 1 divided by negative 1. And so what happens is these negatives can cancel, and I get t to the third power all over 3 plus 8 times t plus 1 raised to the negative 1. So I guess I could just write it on the bottom like this, right? And then remember that that is evaluated from 0 to 5. So this is evaluated from 0 to 5. And then mathematically what I would get is I would get 5 cubed over 3 plus 8 over 5 plus 1 minus, that's the upper limit evaluation, and then 0 cubed over 3 plus 8 all over 0 plus 1. Clean this up a little bit. I've got 125 over 3 plus 8 over 6. Got to do a little math on that end. Over here I've got 0 plus 8. Alright. Common denominator, if I make this a 6, this has to become 250. So I get 258 all over 6 minus 8. And then how many times did 258 go into that?
43.
Yeah, it was 43 times, so it was like, I said that wrong. So how many times does 6 go into 258? And then 43 was the answer. And so we got 35 was was the thing. But now, was that the total distance that was traveled? So that's basically example number 2. And so part of the problem with this is, when we graph this, I'm going to have a positive value and I'm going to have a negative value. That represents 2 different areas under the curve. One of them is below the x-axis and one of them is above. So how do I determine the actual distance that was traveled?
Absolute value.
Well, the key is distance traveled, we almost always associate that with an absolute value. So if you think of a number line, basically we had, if you recall from examples 1 and 2, we were told in example number 1 that we started at 9 centimeters, right? And then we went back a certain distance, and then we moved forward a certain distance. And we wanted to figure out what that total distance was that was traveled between 0 to 5 seconds. Okay? We also established that right here, this occurred when v of t was equal to 0, because we established that the acceleration of this thing was always positive. Right? So we have a distance from here to here plus whatever, somewhere down here at, so this is like, this is at t equals 0, this is at t equals 5, and we're not quite sure where that was, but if I remember correctly from the example, we said at t equals 1.25, the velocity was equal to 0. And so just to recall where this is all coming from, if we go back, and I still have it in there, and we look at the graph. Basically, this is the velocity. So at t equals 0, my velocity was here. In fact, let's trace that. When t equals 0, my velocity was at -8, right? And then we said that when t was equal to 1.25, my velocity was basically 0. It was like 1.25, something, you know, it was rounded. And then at t equals 5, we found our velocity here. We also established that our area under the curve was 35. So let's do a little math and see what's going on. What is this area under the curve right here? Well, let's see. So we know that it's going to go to about 1.25. So we're gonna approximate. So I'm going to hit. I'm going to go to my calculation menu, and I'm going to hit option number 7, and my lower limit's going to be 0, and I'm going to go up to 1.25. Okay? Notice that it's about -3.79, right? Now I'm going to go, and I'm going to evaluate, what do I plug in next for my upper and lower limit? Oops, wrong thing. Let's do this again. So, what am I going to plug in for my upper limit? 5. And so I've got about 38.79. What does that add up to?
42-ish.
Yeah, so what we have here is we have this area under the curve here that represents a distance, but it was -3.89 or something like that, right? And so up here, what did we have? Up here we had 38, and this is 38.8 roughly. So this means that I moved 38.8 centimeters in the positive direction. This means that I move 3.89 centimeters in the negative direction. What was the total distance?
42.
Roughly, yeah. The textbook says 42.59. Now, how can I do that, though? Is there a quick way? Am I doing this? So how could I do that?
With the original function and the y equals an absolute value bracket.
Yeah, watch this. If I take, whoops. If I take my original function here, and I put this in, there's two ways to do it actually. But if I hit second delete, which lets me insert, and then I go to math, oh no, maybe it's just, oh yeah, go to number and go to absolute. And I put that in parentheses. I know it looks a little crazy because I got the drawing on there, but I want to leave the drawing on there. And just take a second for that to, now watch what happens. What it's going to do is it's going to take this part here and flip it up. So there, at one time, these were all y values, and these y values were negative, but because I put it in absolute value brackets for the whole function, what it does is it flips this whole thing up. So now I can get the sum of both of these by calculating the area under the curve from 0 to 5. So my lower limit is 0, my upper limit is 5. Now watch what happens. And by the way, the area right here is the exact same area as it was when it was flipped down. We just took these negative y values and flipped them to positive y values, but the area is the same. Does that make sense? So this is a quick and easy way to get the total distance it traveled. So the total distance that it traveled, so this is not the total distance that it traveled. That's the final position. Okay? The distance that it traveled is, it went here, it started at 9, and it ends up at 35. So the distance here is 35 when t equals 5. But it went back so many, and when you add it all up, you end up with 42.59. Was it centimeters? Does that make sense to you guys?